closely related to the last video where we talked about converting from polar function to rectangular function, or even polar coordinates to rectangular coordinates and vice versa, is the way we will tend to use polar functions in calculus, which is they are much easier for us if we deal with them as parametrics. And this is going to look very similar here to the rectangular conversions. The idea of it being that we said for rectangular, x equals r times the cosine of theta. Well, if r is a parametric function, such as f of theta, we just replace r with that, and that gives us the parametric x. And then, since y is r sine theta, if r happens to be a polar function, I replace it, and that's my parametric y. So, for example, if we had r equals sine of 6 theta, which gives us this 12 leaf rows, or 12 petal rows, then to change it into parametric, my x would be this r times cosine theta. And then the y parametric would be this r sine of 6 theta times sine of theta. And if we graph that parametrically, we actually get the exact same graph as if I graph the polar function sine of 6 theta. So this is just parametrically doing the same thing as the polar. But the reason the parametric is easier is now that makes derivatives much easier. So if you remember, when we were doing derivatives of parametrics, if y and x were in terms of t, dy dx would be dy dt over dx dt. Well, it's the same idea here. If I change a polar function into a parametric, instead of being with respect to t, it's with respect to theta. So to find dy dx, I would do dy d theta over dx d theta. So for example, if we are looking for the equation of the tangent to r equals 2 sine of 3 theta, when theta is pi over 6, the first thing I would do is change this polar function into a parametric, which my x is whatever r is, 2 sine of 3 theta, times cosine theta. And y is my r, 2 sine of 3 theta, times sine of theta. Well, now, to find the equation of a tangent, that means I need the equation of a line. To do that, I need the point and the slope. So if I do the point first, I just plug pi over 6 in for theta. So when I plug that in, sine of pi over 2 is 1, times 2 is 2. And then the cosine of pi over 6 is radical 3 over 2. Multiply that out, I get the x-coordinate as radical 3. Again, plugging in pi over 6 for theta in the y's, I get 2 times 1 times a half, which is 1. So my y-coordinate is 1. So here is the point in which this is then passing through. Then we have to find the derivative, since we need the slope of our tangent here. Well, to find dy dx, because this is now parametric, I need the derivative of y with respect to theta over the derivative of x with respect to theta. Well, to find dy d theta, I am going to need to use the product rule, which would be then 2 sine, 2 is a constant multiple, then first sine of 3 theta times derivative of sine, which is cosine, plus the 2 times sine of theta times the derivative of sine 3 theta, which would be cosine 3 theta times 3 because of the chain rule. And then to find dx d theta, I need the derivative of this, and I'll need to use product rule again, which would actually give me negative 2 sine of 3 theta sine theta plus 2 cosine theta plus 3 cosine 3 theta. And we're interested then in the value of this when theta is pi over 6. So when I plug pi over 6 in for theta, I get that my slope is negative radical 3, which then means that our tangent, because we know the point and we know the slope of the tangent, would be y minus 1 equals negative radical 3 times the quantity x minus radical 3.